Hello everyone, welcome back to the tutorial 2. This session which will be covered by Dr. Sai Teja from Field Application Unit OPAL-RT. Sir is going to talk on basics and demonstration of power converter control with OPAL-RT. Before handing over, I just introduce to all of you. Sai Teja completed his Bachelor of Technology in Electrical and Electronics Engineering from Aditya College of Engineering, and his Master of Technology in Power Electronics and Drives from Gayatri Vidya Parishad College of Engineering, Visakhapatnam. He worked on various projects dealing with motor drive kit application for achieving the HIL simulation for PMSM, induction motor, and DC motor, to name a few. He joined OPAL-RT Technologies India in May 2021 as Field Application Engineer, and he is currently working with various clients, including PG and research scholars from IITs and NITs and other educational institutions in India, and working closely with the people from industries like Caterpillar, Eaton, Tata Motors, L&T for validation of their control algorithms in real-time simulators. Thank you, Sai Teja Garu, for accepting our invitation and handing over to session to Sai Teja Garu. I just stop this sharing the screen.
Yeah, thanks for the introduction, sir. I'll start presenting now. I will share my screen. Hope my screen is visible, right? Hello, my screen is visible now, sir.
You are visible, sir.
Thank you.
It's visible.
A very good evening to one and all. My name is Sai Teja. I'm working as a senior field application engineer at OPAL-RT Technologies. Today, I'd like to give you knowledge on basics and demonstration of power converter control using OPAL-RT. So this is the agenda for today's presentation. I'll explain about our OPAL-RT company and then basics of real-time simulation, followed by OPAL-RT's how to use the OPAL-RT simulator for achieving power converter control as well as a EV powertrain. Finally, I will share with you a demo of onboard charger application using OPAL-RT HIL system. Coming to our company overview, OPAL-RT is the world leader in development of real-time digital simulators, and all our simulators has technology of both PC and FPGA. And these simulators will be using for rapid control prototyping and hardware in the loop application. These operating systems are mainly deployed for design, validation, and optimization of complex control systems. Our company was founded in the year 1997, and as of now, we stand at around 400 plus employees worldwide. And we have a local office worldwide, like in India, we have in Bangalore, and then in US, we have 2 to 3 offices. Like that, we had office in German, China, Japan. And one good part about OPAL-RT is every year 20% of the revenue we achieve will be reinvested in R&D, so that every year we'll come up with a new platform for both hardware and software to cater the growing application complexity of the systems to cater new industries. So we provide high-end real-time digital simulators, scaling from compact portable devices to large integrated test benches. In the coming slides, you can see what are these test benches and what is the application of it. So all these technologies systems are powerful, flexible, and scalable. So these are some of the two software tools we have specially designed to cater applications right from power system till power electronics. So first I'll explain the overflow or the workflow of OPAL-RT system. So it all starts with designing the model offline. So we have two softwares. One is Atilab and one is HyperSync. For Atilab software, we'll be having a backend MATLAB model which will be executing on the target. So the model will execution will take on the real-time simulator. Whatever the offline first the design of the MATLAB model is done, will generate a Linux compatible code which will run on these real-time systems. Then each and every target will be having analog and digital channels using which we can connect to an external physical controller. So this setup is known as a hardware in the loop setup. And then the feedbacks of this, depending on this communication and the results we got from this plant and the controller, if we are finding an issue with either plant or control, we can again go to designing the model and recalibrating the controller or the plant till the desired results are achieved. So this is the complete workflow with OPAL-RT system. Any OPAL-RT system you take, this is the workflow we follow in order to start your project, where test and validate your project. Now, coming to the real-time platforms we have. So we have a compact system named as OP4512, and this is a mid-range product OP4610XZ. And then these are our high-end simulators 5705 and 5707. All these simulators has both technology based on FPGA and CPU, whereas this OP5033XG, this platform has only CPU based system. So on this, you can this will not have any IO cards. You can happily run your model and validate whether it's running in real time or not. The remaining simulators has both CPU and FPC technology. So now I will explain about the architecture of the simulators. So this architecture is generic for all the platforms. So we'll be having a DUT, and here on this RT simulator we'll be running a plant. So as you see, each and every simulator will be having two processors. One is CPU and one more is FPGA. So if you see, this we call it as a host PC. This is the place where a user will be developing their model. Once the model is designed, so we'll be having TCP IP based communication to send this model from this host PC to the real-time target, real-time simulator. And once it's sent here, the model will be executing on this CPU processor. So this is where the processor will be having the real-time OS required software, and the model execution will be happening here. Then we'll be having a PCI based bus using which the data of the model will be sent to the FPGA processor. Why FPGA is required? It serves two purposes. One is driving the signals from CPU to the IO card, and one more is for fast power electronic converter based application will be running those models on the FPGA processor. I will explain about that in the later slides. So one of the application of FPGA is to take whatever the data that the model are running here, it will take the data and send it to these IO cards. So why FPGA should drive these IOs? Because when we have a device under test, the data latency or the time required to take this data, send it out, and then take the feedback, give it back to the model should be as low as possible. With FPGA processor, all this communication will happen within 2 to 3 microseconds. The delay is very less. So with this kind of a faster system, we can have a very tight catch-hold between the DUT and the real-time simulator. That is why we'll be using the FPGA for driving the IO cards. So you can see all simulators generic configuration will have one analog input, one analog output, one digital input, and one digital output. So let us say I have a power converter control logic running here. So depending on the voltage or current waveform of the converter, it will take as an input, and it will generate the gating pulses depending on the error. So those gating pulses we can read it as a digital input and provide it to the plant model. This is how one can achieve a closed loop HAL testing for a power converter application. And it's the same for any application actually. The device under test can be anything. The required appropriate plant should be running here, and by using the IO channel, today I can use it for an FOC control of PMSM motor. Tomorrow we can use it for DTC control of induction motor. So we can use the same simulator for a number of projects. That is one of the better place for real-time simulations. It will help you to test and validate different control algorithms in a very faster way. And as I told, all the systems are flexible. So today I'm having only one set of analog and digital channels. Tomorrow, for a different project, if I have to go for more IO channels, we just have to add one IO expansion box. So this main simulator will remain the same. So you can just have an IO expansion box on which you can mount the required IO cards, and then just start sending the signals from the IO expansion to the DUT. So all these are scalable and flexible solutions, and it's the generic architecture of OPAL-RT simulators. If anyone has any doubt, you can happily stop me in between and clarify. I'll be happy to clarify your doubts. Now I will explain about different kinds of real-time simulations that are basically available in this technology. So whenever, let us say, I have an MATLAB model and I'm running it in my system, we call it as offline simulation. Then coming to the real-time applications, depending on the way we are doing the simulation, we have these four types: model in loop, rapid control prototyping, hardware in loop, and power hardware in loop. We'll see about all these applications one after another here. So the first phase of testing in a real-time simulation will be model in the loop simulation. So the purpose of this is we can tell it's for proof of concept. So here we'll be having the control logic and the plant model both simulated and running on a real-time platform. Why we have to do this in this as it's like a proof of concept. So one will be executing the project and verify that whether the plant response is in accordance to the control or not. So here both plant and controller are simulated. So once it will help you to understand the functionality description, and it's we can tell it as a preliminary study. Once this is done, depending on the availability of the physical system, we can either go for rapid control prototyping or hardware in loop simulation. So coming to rapid control prototyping, as the name suggests, we'll be going to test the algorithms of the controller. So here we'll be going to have the controller simulated and connected to a physical plant. So in this way, one can refine the algorithm of the parameters. We can do the open loop testing here. We'll be running the controller and we'll send the gate impulses to the real plant. We can do the closed loop as well. We will take the feedbacks of this real plant. We need to scale it down in order to send it to the IO channels and verify in closed loop whether the plant response is in accordance to the simulated controller or not. So here we're going to connect the simulated control to a real plant. Once this is done, this is like hardware in loop is one of the application which is used by most of our clients worldwide. So here this hardware in loop testing will help you to test the final controller in safer conditions. So this will help you to prepare the controller for final physical test. In this testing, we'll be connecting a real controller to a simulated plant. So here what happens, we'll be going to apply different kinds of fault on the simulated plant and see the controller response. How whether the controller is able to detect the faulty cases of the plant and it is able to take the right decision or not. We'll be going to test it in this hardware in loop testing. As the plant is simulated, we need not have to worry for the various cases what will happen whenever you're doing some fault study. So let us say if I have a motor controller, so if it is a physical motor and if I want to short a phase on the motor, we all know it will result in hazardous situations. But here in hardware loop testing, as it's a simulated plant, as the motor is simulated, we can happily do fault studies on the plant and see the control response. So this is the case where it finds the wide range of application in our studies for hardware and loop testing. Now, coming to the power hardware in loop testing. So this is before going to the physical testing, this is we can tell an advanced level of hardware loop testing where along with a real controller, we'll be going to include a real some part of real plant as well into the simulated environment. So the best example here I can show you is let us say I want to do renewable penetration into the existing grid. So I have some renewable based plant which is simulated in the model along with the existing grid. In order to verify the controller response with a real renewable plant, so let us say I have a PV farm. In that, I can have one solar PV inverter, physical inverter connected to the simulated plant. How this is achieved? We are having 4 quadrant power amplifiers, which will help in including these solar based PV inverter or an DFIC based wind generator into the simulated plant. So this will take care of bidirectional power flow along with scaling of the signals. So whenever we're connecting this real PV inverter to the plant, so it will take care of stepping down those voltages to the signal level and feeding it into the model. And whenever the controller is giving the commands for bidirectional power flow, these signal level data will be converted to power level and fed back to these inverters. So in this way, along with the test of the external controller, we can verify the performance of this solar inverter, whether it is in accordance to the simulated plant or not, whether the responses from the simulated PV inverter and the real PV inverter are same or not. We can test in safer environment, then proceed for commissioning this real controller into the real PV farm. So nowadays, these power hardware and loop testings are picking up the pace, and most of the research institutes, both in academics and also in industry, they are going forward to test their control algorithms in this PHIL environment before as a validation step before going into the physical testing. So this is about power hardware in the loop simulation. Now, coming to this specification of the analog and digital I/O boards, we have our analog channels. Analog cards will come with a 16 channel each card, and digitals will be a 32 channel each. We can see the voltage ranges. We can have different for analog output plus or minus 16 volt, or analog is plus or input is plus or minus 20 volt. Whereas if you see the current rating will be in milliampere, all these are PCBs. So one has to ensure that they're not sending more current, which result in damage of these I/O boards. If we want to send some 5 ampere or 10 ampere, we need to have one more module which will take care of that signal conditioning. And communication protocols. So if you take an automobile application, in most of the automobile, they'll be having this CAN based protocol or EtherCAT based protocol. So our simulator has the feasibility to send the data in these communication formats. So if we take a power system or a microgrid based application, there for smart devices, one might have to use or send and receive data from those smart relays using these ISC 61850 goose and sample value, or C37.118 slave master protocol. And sometimes you might have to use this TNP or Modbus or serial RS232 or RS485 format. Our simulators has feasibility to send and receive data in all these formats. This is a partial list, and we have some more protocols as well. So depending on the application, user can select what kind of a communication protocol they want and enable it on the simulator, so that they can start sending and receiving the data in that format. And we have some third-party hardwares as well. This synchronization, whenever you are having these smart devices, you need to have that data transfer with a reference clock. So we can have a reference clock with the IRIG-B format or 1 PPS signal or IEEE 1588 base format. So we have our hardware, as I told, our solution is flexible. Depending on the requirement of the user, we can configure and send and receive data in all these different protocols. So these are some of the software products what we have depending on the application. So this ePhaser sim is a solver which will work in a phasor domain, and it finds application whenever you want to study the transients that are occurring in a grid level. So when I told grid level, so you'll be having more number of buses in the system. So you can see a number of nodes. So you can simulate a total of 20,000 nodes. Then HyperSim is our standalone software, which finds its application in large-scale power system domain. So most of the utilities and manufacturers, they'll use this HyperSim software for testing and validating their power system. So it's a EMT-based software. And this eFPGA sim, so this is the solver which will help you to run a power electronics based converter on the FPGA. So this is what I told initially. FPGA has two purposes. One is to send the data via IO cards, and one more is to simulate this power electronics based simulation on FPGA. So here you can see the time step will vary from 1 microsecond to hundreds of nanosecond. Nowadays we have one more fifth generation of this solver which will go in picoseconds as well. Why this kind of time steps are required? So if you want to run a converter in 50 kilohertz or 100 kilohertz of a getting pulse, we need to the time step should be at least 20 times of that switching frequency. So the model should run in nanosecond in order to able to detect that take that gating pulse and do the correct action accordingly. So that's where this EFPGA sim helps all power electronic researchers to simulate and validate that controller in a nanosecond time step. So as today's discussion is on providing our application oriented towards power electronics, I will explain a bit more on this eFPGA toolbox and how it helps the user to run their model in nanosecond. Along with a demonstration, I will do that. So yeah, here if you see in hardware in loop testing, as I told, a real controller is connected to a simulated plant. The whenever you're doing a power electronics based study, this simulated plant normally it may be having a power converter or a power drive. Along with the converter, you might also have a motor. So this plant must run as fast as possible in order to take these PWM pulses as an input, do the required simulation, means driving the converter and then the motor, and then provide the feedback back to the controller. So the voltage or analog voltage or current feedbacks, along with the speed feedback. You can have this Hall effect based sensor or encoder. You can have these for sending the speed of the actual speed of the motor data. So in order for the controller to generate high switching frequencies, this feedback should be provided in an appropriate time. So that's where we have this electric hardware solver, EHS. It's abbreviated for electric hardware solver. So what it does is, so it will take the circuit model. So it might be an SPS based model or PSIM based converter or flex based model. So it will directly take that converter, and the best part is it will automatically do that code which is required to run the model on an FPGA. So normally, if you want to do the modeling on an FPGA, one need to have a knowledge on how to write the code in VHDL, or they need to know how to use this Xilinx-based block set which is available in MATLAB Simulink. So it's not a straightforward because you need to have all the converter response written in an equation based differential equation based equations. The FPGA will understand only that. So even though one doesn't have knowledge on all these, like we need not have to have knowledge on the mathematical modeling or FPGA expertise or VHDL programming. We'll just do our converter and motor connections in the normal SPS based modeling. This solver will ensure to convert it and make it run on FPGA. So it will take care of your model code generation, which can happily run on this FPGA processor. So with this, it allows us to have a comprehensive circuit editor, takes advantage of FPGA performance without any code. We need not have to run any code. That is where this solver finds its application in all places where people want to test and validate power converters and motor drives. So now, as the world is moving towards this hybrid EV or EV based vehicles and all, our real-time simulator, as I told, it has a CPU and an FPGA. So we are also moving into same trend to provide a solution for these EV applications. So you can see we are having a multi-core CPU where on the CPU we can run the model of an vehicle dynamics or engine model. Then on FPGA will be running the powertrain part, have the data transfer between these two and simulate the whole EV, connect it to the EV controller and test and validate. EV controller, it might be an MCU plus telematic or any control you have for the vehicle, you can test and validate it. So the fast motor dynamics are simulated on the FPGA with the time step in order of microsecond or sub microsecond. So why we have to go, you can happily understand it by this. So let us say I'm having my powertrain running on a CPU. As I told, there will be all the data will be sent via IOs. So via this PCI link, first it will go to the FPGA processor, then it will be sent to the IOs, and the ECU, the engine control unit, will generate some gate impulses or do the corrective action, and then again from these IOs it will go to the FPGA, and then from FPGA it will come to the CPU. So here the overall latency will be 40 microsecond. So with this kind of latency, we can hardly go with a switching frequency of 2 to 3 or maximum 5 kilohertz frequency. Whereas when we run the same powertrain model on a FPGA processor, as the model is running on the FPGA, it can be directly sent to the IOs and to the external controller. There is no time delay for taking the data from the CPU to FPGA and then to FPGA to IOs and all. All this will be eliminated. The data will be taken from FPGA directly to be sent to the external controller, and the feedbacks as well, or else the whatever the response from the controller, it will be directly read on this IO, then give to the converter which is running on the FPGA. Here you can see the feedback latency will be just 1 micro or 1.5 microsecond. With this kind of feedback latencies, we can happily run the converter in hundreds of kilohertz of frequency. That is where for any motor or power electronic based converter study, will propose the user to follow this architecture or to start using these solvers. So here we can see the whole powertrain, how we are going to simulate. As I told, the controller might require the current or the voltage feedback along with the motor position and speed. So our simulator can provide all this data via analog and digital I/O. So the plant here, including the inverter motor, are modeled on an FPGA processor. So with one FPGA today, as I told, I can go for testing a PMSM drive, tomorrow an induction motor or SRM motor. So we can have various converter topologies and motor designs. We can go for fault and non-ideal behavior simulation. This is important. So when we are doing the physical testing, we will not go for fault studies or non-ideal behavior simulation. So until and unless some fault happens, we are not sure how the controller will respond or what happens to the plant. But here in this hardware in loop approach, we can happily do the fault study. Why? Because this inverter and motor, everything is simulated. So I can happily short a one leg of the inverter by sending the same pulse to the top switch and the bottom switch. I can see under this fault study how the motor will work, or what happens to the motor. So all this non-ideal behavior and all we can happily simulate and study for various topologies. So now, when I'm speaking about an onboard charger, we all know now the trend is towards going for high switching frequencies. So when I want to go for high switching frequencies, the physical material, whatever we are using for the switches, should be able to operate in those region. So here we can see silicon carbide and gallium nitride switches. You can see the characteristics. So silicon carbide we can happily go till hundreds of kilohertz, and gallium nitride, even though the power rating it might go till only 1 kilowatt or till 10 kilowatt, but the switching you can go in megahertz as well for gallium nitride. So silicon carbide it will best suit for an traction inverter based application where the rating of the inverter can be from 15 kilowatt to 400 kilowatt, whereas these gallium nitride will find its application in EV charger or for PV booster and inverter applications, where the overall power range or the power required might not be high, but we can operate it in more higher switching frequencies. These devices has a wide band gap and critical electric field allow high voltage device with thinner layers. So it will help in lowering the resistance and associated conduction losses, low leakage, and a robust high temperature operation. And this has a large thermal conductivity. So as we can see here, the silicon carbide it can go for high power operation with simplified thermal management because it has a large thermal conductivity. So as we are going for the thinner layers and the lower specific on resistance, so it will help us to have the whole packing of this power converter. We can have it in smaller form factors and with reduced capacitance. So it will help in operating at high frequencies and reduce size passives. So because of these features of the silicon carbide and gallium nitride, nowadays for onboard charger, EV charger or traction inverter, people are moving towards these techno switches topologies. So now coming to the onboard charger. So in onboard charger plays the role when we have a physical grid AC terminal and you want to charge the DC battery. So onboard charger will help you in converting first AC with AC to DC, and again we'll be having one more DC to DC converter which will help you in charging the battery. So in that AC to DC conversion, it will take care of power factor correction along with most of the time we'll be having a VNR rectifier or it will not be, it's a uncontrolled rectifier basically. After that, you'll be having one boost followed by an LLC filter kind of a topology. So you can see here, this is how an onboard charger will be there. So the AC plug for charging will be there. So initially you'll be having this rectification, then power factor correction. Then for isolated DC-DC. So for isolated DC-DC, you'll be having an uh, topology similar to LLC converter like that, which will provide you DC to DC conversion along with isolation. So isolation plays a crucial role here because you can always save your battery whenever anything happens on this AC side. So if it is a DC charger, then all the circuit will not work directly. The DC plug-in will happen here, and then it will directly go to the battery for charging. This is how the DC charging will take place. If it is an AC charger, the onboard charger will work here. So most of these plug-in PHEV vehicles or full electric vehicles will be having these OBC application. So here this shows you the OBC charging times. So if it is a battery electric vehicle or a plug-in hybrid electric vehicle, you can see the AC charging battery charging time is related to the charging power and battery size. So if it is a 3.5 kilowatt and if it is a plug-in hybrid vehicle, so it will take around 7 hours for charging this 3.5 kilowatt. But if kilowatt hour capacity of the battery, 35 kilowatt hour of capacity of battery, if it is a 100 kilowatt hour battery electric vehicle, the AC charging port, it will take around 20 hours to complete fully charge the battery. So as these charging times are more, so nowadays for fast charger applications, you are having DC chargers, which will, as there is no conversion of AC to DC, and those DC chargers will happily charge this 100 kilowatt hour battery within 3 to 4 hours. But this OBC will help you in bidirectional power flow as well. In sorry, only bidirectional V2G and G2V application, you can have this OBC. So this how the controller look like for this OBC. Most of the time you'll be having these AC input basically. So here you'll be having a PF for this primary rectifier side. You'll be having a primary microcontroller for AC to DC conversion followed by DC to DC conversion. Most of the time, as I told, this rectifier will be uncontrolled, whereas this boost chopper will be controlled. Once it is done, you'll be having the drivers for this LLC topology. Uh, and as I told, there will be galvanic isolation between this AC side and DC side, the battery side. The secondary microcontroller will take off charging the battery. So the power electronics challenges in automotive will be one, in the vehicle integration, the converter design must be very compact. So in automotive, as you know, in electric vehicle, the overall weight of the vehicle, the battery pack will be the heavier component. After that, it will be this converter and the isolation transformer and all. So the converter design should be as slick as possible, and it should be having a higher efficiency in thermal connectivity should be very efficient, and it will help you in loss management. And the reliability is a key for any product, so it should have a high reliability, means so that it will work for more time. So there should be very less current ripple and all these before going to testing in the physical world. People will be simulating and working on their new device control topologies or new converter topologies. They'll be simulating all of them in this real-time simulation environment and test and validate them. So if you see this LLC based resonant converter working principle, so after the primary AC to TC conversion and followed by the boost chopper, will be having this LLC tank. So the leakage inductance and the magnetizing inductance of the transformer winding will provide you a double L, and you'll be having a resonant capacitor here, which will be working at so let us say if the switching frequency of this half bridge is at 300 kilohertz, we'll try to have this LLC resonate at 200 kilohertz, which will help you in reduce transformer size and charge the battery. So the power transfer will happen depending on this LLC resonance frequency, and the step up and step down of the voltage will happen. Step down of the voltage will happen. Let us say if I have a 600 volt DC bus here, and the battery pack is at 400 or 300 volt, so that step down will happen and the battery will get charged here. So this is one of the success story we have. So we have a client named Value. So they used our OPAL-RT based simulator for testing their onboard charger for a vehicle. So what's the problem? They want to have this plant with general issues for OBC like a variable grid or line impedance. Then they want to go for voltage dip and harmonic and load profile, harmonic injection and immunity. And then they want to test this vehicle to grid, grid to vehicle, vehicle to home. So all these V2X functionalities they want to verify. So they want to validate their control loop, the controller board, and the software part. So what OPAL-RT played here, we provided the solution, optimized the simulator, both hardware and software, to meet their switching requirements, the time constant filtering, component value variation. So by changing the component values here, let us say whenever a switch is closed, so the current will be flowing, the on-state resistance will be very low, and whenever switch is open, the resistance will be very high. So here the component value variation is whenever the pulse is high and switch is closed. So you want to open the switch at that instant. What we can do, we can create a scenario wherein during the on time, we'll make the resistances very high, so that even though the pulse is high, the switch will be open, or vice versa. When the pulse is low, let us say I have the two switches of an leg. So these two switches at a time, only one will conduct and the other will be open. So during the conduction of one switch, I want to create a short circuit fault on the leg. So I have to close the other switch as well, even though the pulse is low. What I can do, I can make the resistance of this switch during off time as very low, which will help in closing the switch and making it like a closed switch. And I'll be able to create the short circuit fault. In this way, we can do that switches open and close whenever we want by changing the resistance of the switch. And along with this, we can have different values for the load resistance during the functionality of the converter. So in that way, we can start changing the values on the fly and verify the robustness of the control and the software developer. So once we have a fine-tuned controller and software, it will help you to integrate to the hardware without any failure. So the overall aim of this solution is to make your control and software robust enough in order to integrate it properly with the hardware without any failures on the hardware component. So this will help you easily to detect the plant issues, wherein we can inject the real plant issue and simulate the full behavior and come with the case study, what went wrong or how to improve on that failure. So this is one of the success story we have in recent days with this OBC power stage power controller testing. So why resonant converters are becoming a standard? Because these are compact, efficient, and you have a high power density design. So these are some of the advantages which helps in finding these resonant converter topologies in onboard charger application. So these are some of the differences one can have between these voltage source converter and resonant converters. So voltage source converters, we know they will be working. The control strategy will be pulse width based control, amplitude control, whereas resonant converters. So PSCs most of the time might be a inverter, a DC to AC, or depending on the power injection, it can convert AC to DC as well. Whereas most of these resonant converters will be DC to DC converters, and here the control strategy will be mainly based on the switching frequencies. These are all frequency controlled converters. Here you can see the gating frequency will be in few kilohertz, at most 100. I can't tell. They will be normally operating at 100 kilohertz as well. We can go up to some 25 30 kilohertz here. Whereas these resonant DC-DC converters, they switching will start at 100 kilo, and it can go up to some 400 kilo, 500 kilo like that. So when we are going for this 1 kilohertz to some 20 30 kilo frequency, the simulation challenge will be for getting the accurate amplitude of the device. Means the feedbacks should be we need to measure these accurately the amplitude applied. Whereas in this resonant topologies, getting the right frequency applied is important, because depending on the frequency only we are going for the next pulse, so it will help in avoiding the aliasing and ripple effects. So here for both these converters, we have so the generic solver AHS will cater. So as I told, we have two generations of this solver as generation 4 and generation 5. So we'll be using this generation 4 solver for this fast model loop, like 100 times of switching frequency. We can have the plant running, and we can have for Gen 4. Whereas this Generation 5 solver is specifically designed to optimize and work with these resonant converters, where the model loop rate will be very high, and it will be, as I told, it will be from nanosecond to picosecond. So it will be having very high resolution capture of switching events and compensation for the model. So you can see here, this is a slide on this generation 5 of our EHS solver. So this is help you to deliver the most powerful real-time simulator. So here, depending on the topology of the converter we are using, it can go down from 90 nanosecond time step for user-defined topology, and the gate oversamplings and all, the switching event compensation and all, we can have at a step of a picosecond, and it has fifth order discretization, and this is the fastest real-time reconfigurable power electronic solver available on the world as of now. So in marketplace, I can tell no other simulator can beat OPAL-RT in terms of this high switching frequency or power converter based application. Okay, these are some of the, as it's a fifth order discretization, you can see we are able to capture very good switching composition events with this fifth order solver. It will be more accurate, I can tell that. So one part of our power electronic converter will be like having a AC to DC or DC to DC inverter. So finally, you'll be having a uh, plant as well. As a, if you see an EV, you'll be having a battery pack and also a motor along with the power converter. As I told, whatever the variations that are happening on a battery will not be that much fast. So battery, it will be in millisecond. The response will be either in millisecond or in seconds. So one might not have to have a battery running on a FPGA solver. We can happily run it on a CPU, whereas this motor will be connected to our power converter. So along with the power converter, we should be able to run our motor on a FPGA. That is where for our EHS solver, we have a dedicated library of machines. So you can see here the machine block will be something similar to this. where the user has the user can happily give the value of their machine topology, and once it is executing, it will take these values and start working as that particular motor. So user need not have to spend their time in modeling the machine. We have predefined library of machines. The user just have to provide the inputs of that machine, and it will start working of that configuration. And whatever, as I told, along with the converter, whatever the motor you're configuring here, it will be executing on the same FPGA processor. So some of the machine library we have. So in a permanent magnet synchronous machine, we have IPM or BLDC or SPM. In induction, you can have double fed induction generator or a double fed induction motor or a squirrel case induction motor. We have block for switch ratings motor as well. So these are different machine configurations which are available in our library. You just have to provide your values. And as a motor as well, it's a key component in a vehicle. So we have finite element analysis based solvers for specifically designing a motor. So why we go for FEA analysis tools? There we can include the effects of rotor asymmetry or back EMF harmonic for a PMSM, saturation effects or the cogging torque effect. So in a normal machine model, we can't include all these dynamics or various asymmetrics of a motor. So if you want to bring in this motor data from these FEA analysis tools, we can happily bring in those lookup tables. So if you take this ANSYS Maxwell or MotorSolve or JMax software, so there you can include all these asymmetrics, and finally these tools will provide you outputs in the form of either lookup table or JSON files of this motor. So has the capability of our solver has the capability of taking in those asymmetric motor data and directly run it on the FPGA solver. So you need not have to worry about different motor configurations. If you are using FE based tools as well, you can happily import these spatial harmonics or some asymmetrics of this machine directly import into our solver and start. The solver will make sure that it will run your motor with those dynamics. So along with this motor data, if one wants to bring in the dynamics of a electric vehicle as well, so you have these some softwares like the Gamma Technologies or CarSim or AVL, which will help you in including the vehicle dynamics. So you can directly add those data also into your project and start working with it. So these are some of our user. This one is from Toyota and Mitsubishi. So they are using our solution, OPAL-RT's electric motor FPGA solution, to test and validate their electronic control unit for a double PMSM HEV motor, hybrid electric motor for Toyota players. So these are some of our success stories. Our simulators find their application in ARI. So ARI is the testing agency in India. So any whatever new vehicle you're seeing on the road, it should go. We have 2 to 3 testing agencies. It should be certified from them before it come on the road. So ARI use our simulators. So as I told initially, these are kind of a test beds where along with the simulator we'll be doing all the required signal conditioning and include some third party devices in order to make this bench suitable for the client application. So it's a generic automotive test bench capable of interfacing a HEV or EV along with a BMS ECU as well. And we have other clients like Rivian, Volkswagen, General Motors, and all. And this is one more hybrid bus ECU testing integration testing unit we delivered in Tata Motor for their hybrid bus ECU validation. So this testing is helpful for them in testing their hybrid ECU, EMS, TCU, and EBS unit. So, as I told that P-Hill application for an electric vehicle, the power hardware in loop, one can test their traction inverter. So, the traction inverter is a component. So, in this P-Hill, what we'll do, we'll be going to test this traction inverter in power level. So, there will be hi-fi motor emulation will be available in order to validate the functionality of traction inverter in power level. So this overall concept is we'll be having a motor emulator. So what we are going to do, whatever the motor characteristics we want, we'll be first simulating on the OPAL-RT system. Take out those motor characteristics and feed it to this motor emulator. So these emulators will be ranged in a few kilowatts, starting from 60 kilowatt. It can go up to 500 kilowatt motor, and this output of this power level motor will be given as an will be connected to this traction inverter. So that output of the traction inverter will drive this motor. In this way, you can validate your traction inverter whether it is working fine or not in a safer environment. This is a PHAL solution for electric vehicle application. Okay, I hope there are no doubts or you have understood whatever I told till now. Now I will explain you our workflow with a HAL demo setup. So as I told today, I would like to show an onboard charger application. So in an onboard charger, the plant will be having two parts. One is the converters, which will be having AC to DC conversion followed by DC to DC boost and the LLC topology, and then the battery pack. So here, if you see, it all starts here. We are having an single phase AC source. So this is an uncontrolled rectifier, I can tell, which will convert AC to DC. So this DC will be here. You'll be having this PFC control. So it might not. It might be controlled as well, depending on the requirement. So we can control this in order to have a better power factor. Then this DC will be here. You have this boost stage, which will be providing you a higher DC output. So here you have this half bridge topology. So this is half bridge topology with the LLC tank, and the here you're having this this resonant transformer, and you have this galvanic isolation, and the output of this will be fed to this battery. As I told, the dynamics of the battery will be very less. You can see here there is one capacitor followed by a resistor. So we are going to interlink the battery characteristics with this resistor. How? Whatever the current flowing here via this load resistance will be fed to the battery. So if I show you the other model, so you can see this is the MATLAB Simulink model. So I for the OBC application, we have divided the model in such a way. The slower part means this battery pack and all will be running on a CPU core, and the faster part will be running on our solver, EHS solver. So if you see here, we have a dependent current source. So whatever the current that is going through the load, whatever the current that is flowing through this battery will be fed to our converter via this current dependent source, dependent current source. This is how we are going to interlink this battery pack with the OBC converters available. So this is one more software from OPAL-RT. Either we can use this software or we can use MATLAB based model for modeling these power converters. So this software we call it as schematic editor. it will help you in modeling your power converter part and run it on the FPGA. So this is the onboard charger application. And as I told, after the onboard charger, when the battery is discharging, we'll be having a three-phase inverter along with the motor. So this will be your powertrain. So if you see here, we are having a three-phase inverter and a PMSM-based motor. So this will be our powertrain. So this is your full converter. You can tell the full powertrain model of an electric vehicle. So as I told, once we have this MATLAB model, we can directly load it into our RTLab software. So this software will act as a bridge between your offline MATLAB model and a real-time simulation model. So this will help you in running your converter or the plant on the real-time processor. So I'll just take a remote system access here. So I have this model executing. So this is one of our latest development in our software. So we call this as dashboards. So once our model is builded, means once the Linux compatible code is done, so we can happily come to this dashboard and have a user screen like this. So these different screens will show you the responses of different converters and the motor once it is executing. So from this software, I can happily unload the model and see the responses. So here, if you see, I have an external controller for generating the getting pulses. As I told, it's a hardware in loop setup. So I'm having an OP-866 controller, which acts like a DUT, and whatever the PFC plus OBC plus inverter traction inverter and the motor I have shown, it will be running on this simulator. So the responses of the simulator will be provided to this DUT. So here we can see as of now it is charging the OBC, and now I'm discharging. So whenever this SOC is greater than 80%, I can start the motor and run it. So I have given a command of 1000 speed. So here we can see the DC link voltage and the various graphs I'm having for showing the motor torque and the speed and all. And these are the different duty cycle I'm getting from the controller response. So this is one of the demo I thought of showing today. So now, if you have any queries, I'm happy to answer, or else if you have any doubts on the topics I covered till now, I'm happy to answer now. So, does anyone have any doubts or any clarifications you want to know from this today's topic?
You can post the questions if you have. You can post in the chat box, please. Yeah, Tejas, sir, I have one question.
Yes, sir.
Like number of the ADCs in any controller, is it fixed once you buy it, or is there anything like we can configure at any point?
The number of IO channels, sir.
ADCs.
ADCs means, as I told, one card will be having 16 channel for analog to analog input, and analog output will also be 16 channel. But in future, if you want to add more, we can just have to use an expansion box for the same. It is scalable, and also depending on your requirement, if you want more cards, one simulator, this normal simulator, the standard one will come with 4 IO slots. If you want, let us say 32 analog inputs or outputs, you can use place the two cards and configure it before delivery.
Okay.
So in that way, it's configurable.
Like what is the typical the voltage signal which we can give to the ADC?
Its maximum is 20 volt, and we have signal conditioning modules. So if you want to like feed in the let us say the inverter has a DC bus of 600 volt or 415 volt AC, you want to feed in as an input to the simulator. We have one another signal conditioning module wherein you can feed those inputs. It will take care of converting those signals to the level required by the simulator. So there is a conversion from 600 volt to 10 volt, and that signal will be fed to the simulator. Similarly, in terms of current also, as it's in few milliampere, if you want to feed in a signal of 15 ampere like that, we have one more conversion module which will take care of converting that 15 ampere to 10 volt and feeding it as an input.
Okay.
Yeah.
Is there internal protection is there for the any kind of a signal if you are going to higher voltage?
Sir?
Is there any internal protection will be there?
Protections are there. Yes, yes. Coming to the digital, all channels are galvanically isolated, and analogs are also has two types. We have both isolated channel modules and non-isolated modules. Depending on the requirement, we'll provide those cards.
You have any questions like please audience? Make use of day for day. Yeah, please. Sir, there is a question in the chat box, sir. Can you please?
Yeah, yeah. As I told, we have this generation 5 solver of power electronics with which you can have these samplings in megahertz. Coming to the latency, it will be nano to picoseconds. It is specifically designed for these high switching frequency topologies. And we had success story from, as I showed, from Valeo. They tested that OBC at 400 kilohertz in closed loop using this solver and our OPAL-RT simulator. Yeah. Thank you, Srinivas.
When you're going for the controller, is it possible to change the sampling rate of the signal at any point?
Yeah, means on the fly we can change that control switchings and all.
Uh-huh. Okay.
Simulate the BMS. Uh, Most of the time, our our users from the industry like Caterpillar or Tata Motor, they'll be having their own BMS control technologies, and they'll use our OPAL-RT to simulate the battery characteristics actually. So it will be the other way around. So we'll provide customized test beds for testing and validating a BMS controller. Finally, before testing the battery pack, user should understand and see the responses of their BMS controller, because the cost of the battery pack will be very high when compared to the BMS controller. That is where people will have their controller in development and R&D in the development of their control topologies. They will do it on a controller chip and connect it to this simulated battery pack for validating that BMS controller. But yeah, if you want, you can simulate the BMS as well on the OPAL-RT. There is no issue. Hmm. This is a tricky question. Actually, it depends on their requirement, and we are sure like we are compatible in this market segment, and will provide customized solutions. Feel free to contact us. You can write us. I can drop my I'll drop my mail here, mail ID here. You can always contact us, and we'll provide you. We'll first discuss on your requirement and provide you the solution accordingly. I have dropped my mail ID here, sir. Srinivas sir, you can drop us your requirement and we'll get back to you on the solution along with the quotation.
Is there any questions? What is the basic model which you have, sir, presently at the very lowest cost?
Our entry level simulator is OP4512. So
Perfect.
it's, yeah, 4512, and we have one mid range as 4610, and our high end simulator is 5707.
See, with the OP 5
Yeah, 4512.
4512, we can go for a larger having the evaluation in the entire the system automatic. We need to go for the system separately and the plant.
Means for which
Plant and the
application?
country. I wanted to say.
Yeah, yeah. Means we can go for let us say a grid with 30 to 40 buses like that. We can simulate happily. And if you want to have a renewables in that, we along with this simulator, we have specific solvers. As I told, this EHS for power electronic application, and we have one more E magazine for grid integration and power system based studies. Even though the simulator is compact level, once you have these solvers, you'll be able to do a complex model with this simulator itself with the help of these solvers. because each simulator, as I told, it will have both a CPU and FPGA processors. With this EHS solver, you can take out your converter and motor. You can run it on FPGA, and the rest of the plant you can have on the CPU. In that way, you can divide your model and run it parallelly on different processors. You can happily have a complex model simulated with this entry level simulator as well.
As of now, like it is compatible with the present the MATLAB environment, right? The OPAL-RT.
Yes, yes, sir. So it goes like this. Every year we'll be releasing the new release of software, and we're always like a 1 year back to the MATLAB. So let us say this year we have 24 of ATLAB, and we can happily use till 2023B MATLAB. So next year we'll come up with a 2025 release of ATLAB, with which you can go till 2024B of MATLAB. So there is 1 year backward compatibility between these two softwares.
No, I'm not clear on that. What
Ha
did you say?
means we are always like 1 year backward compatible. So with this year software, you can use till 2023B MATLAB with
Okay.
2024 RTLab. Yeah. Next year with 2025 RTLab, you can start using 2024 MATLAB.
Any other questions like? See, in your system, like in the MATLAB environment, you have your own block sets, or whether you
Yes,
opt
yes.
for.
We have some specific block sets for a particular application like this solvers, EHS, eMegaSim and all. And we have our own drivers for using the IOs. And we have the OS solver, which will be like directly taking those MATLAB block sets and start generating code compatible with Linux.
No, the additional blocks which is there with the MATLAB environment.
Uh-huh. Yes.
Can we use those blocks itself only directly, or we need to go and use the OPAL-RT block sets only which is there?
No, no, you can happily straightforward use those MATLAB blocks itself. And along with that, we have specific some 2 to 3 blocks which need to be placed in every model because our solver will understand it in that way
Okay.
in order to generate the code and all. But they are very generic. Once you start using it, it will be very easy to use that.
There is no limitation of your solver with the MATLAB toolbox, MATLAB available building blocks, right?
Yes, yes, there is no limitation.
Any questions? I mean, if people are working in hardware, like you can definitely ask questions to Sai Teja sir. I think like we can stop over here. Yeah, thank you, Sai Teja Garu, for accepting our